Chapter 5 is all about the cell membrane, and part of it is about transport, part of it is about proteins and structures in the cell membrane that allow cells to interact with each other. First, I want to make sure you have a good grip on what a cell membrane is. And if you remember from the endomembrane system video, I talked about all membranes are made up of the same thing. So let's look at what they are made of. So they're made of this phospholipid bilayer. Layer. So bi in biology means two, and we'll look at closer, but these little heads with two little tails are the phospholipids. And you know that a lipid is hydrophobic. It means it doesn't like water. The phospho part, the head of this lipid, is actually polar, so that means it's hydrophilic. It likes water. So the heads here on a phospholipid bilayer are near the water, and there's water inside a cell and there's water outside a cell. So imagine this being 3D, and the phospholipid bilayer is this circle that I'm trying to make all these lines over, right? And there's water outside and there's water inside. So the inside part here is all the lipids, so that's the hydrophobic region. So membranes are made up of excuse me, the lipids in a bilayer form excuse me, and then also all these blue structures are proteins. And in class we'll talk about different types of proteins, such as proteins that go all the way across the phospholipid bilayer. So they stick out of one end and stick out of the other end. That particular guy is called a transmembrane protein. So trans means across. So this protein goes across the membrane. There's also proteins that we call integral. Oops, sorry, just a second. Integral, because they're integrated into the phospholipid bilayer, so they're stuck in there. So here, integral membrane proteins. So a transmembrane protein is also a type of integral membrane protein. And then finally over here we have peripheral membrane proteins. So peripheral, think of on the periphery. So they're not stuck in the lipid bilayer, but they're on the periphery. They're on kind of the edge. And later we'll talk about glycolipids. Glyco is like sugar. So this is sugar pieces stuck to your lipids, and glycoproteins have carbohydrates, sugars stuck to proteins. So in general, a membrane is a phospholipid bilayer with specific proteins in it that give the membrane their function. Proteins give them their function. Oh, and one other little guy I forgot to talk about, sorry, which we'll talk about again, cholesterol. Cholesterol is also a lipid, and we'll talk about why that's important in membranes. Okay, so again, close-up look of your phospholipid bilayer, hydrophobic tail, hydrophilic head. You can just draw it. That's as much art as you need to be able to do. The key is that you're drawing two tails, two fatty acids. And then the head we draw as the circle because it can actually be different things. We get that to those details in cell biology, but this has charge, or at least partial charge, depending on what the head is. Okay, and same here, ditto. And it's this part in the membrane that is the lipid. And this is the part that really, sorry, let me write hydrophobic. This is the lipid part, is really what makes it a barrier. So sometimes people equate the plasma membrane or the cell membrane to like a baggie, right? It's keeping all the contents, the cytosol and all the organelles inside that baggie. But what you need to understand is that that baggie has permeability, which means things can actually cross it. You don't want things crossing your Ziploc, right? Because if you put something liquidy in there and stick it in your bag and go to school, you don't want it to leak. But membranes actually can allow things to cross that phospholipid bilayer. Again, I know I'm emphasizing these phospholipids because they are the key to making a membrane. So again, you can see the polar head, fatty acid, nonpolar tail. So now we're going to look a little bit into more detail. Like this one has a definite kink. And the reason I draw my phospholipids kind of wavy like that is that many of them have these little kinks. Oops. But this definitely is not showing any specific structure. Here, I know it's really super hard to see, but what we have is a C-C double bond. And that causes a kink in the membrane, in the fatty acid tail. So let's look at this a little bit more in depth. So if you remember back to chapter 3, which is your macromolecules, we talked about saturated and unsaturated fatty acids. So fatty acids are just long chains of carbon with hydrogens all around them. Carbon plus hydrogen. Okay. Sometimes we call these tails on like a phospholipid. Okay. And they can be saturated, which means the max number of hydrogens, right? Every carbon, you know, can make 4 bonds. So if you look, every carbon's got 4 bonds and it's saturated with hydrogens. It also means only carbon-carbon single covalent bonds. And saturated fatty acids make these nice long chains. And this is a triglyceride. Ooh, I didn't spell that right. Triglyceride. See, it has 1, 2, 3 fatty acid tails. And saturated ones, because they have these long tails, you can see that they can pack together tightly. So at room temperature, they're semi-solid, right? Butter's not solid like a table, but semi-solid. Because they can pack together so tightly. An unsaturated fatty acid means it has at least 1 carbon-carbon double covalent bond. And once you go from carbon-carbon, which can have 1, 2, 3, 4, 5, 6 hydrogens, to a carbon-carbon double bond that can only have 1, 2, 3, 4 hydrogens, now you're considered unsaturated. You don't have the max number of hydrogens because you have a double bond. Double bonds cause kinks in the structure. If you look over here at this triglyceride, because it has these kinks, these carbon-carbon double bonds, the tails cannot pack as tightly together as they can over here. So C2 take up more space than 2 over here. Therefore, at room temperature, they are liquid, like oil, versus semi-solid, like butter. So animal fats have saturated fatty acid tails. Right? Plant fats are unsaturated. And if you think about your body, this is going to be more liquidy and flowing through your veins and arteries much easier than this, right? So fatty acids that are saturated can start to clump and pack together, and it can cause hardening of the arteries and clogging of the arteries and getting those fat buildups. Whereas the ones that are liquid are much more healthy for you. Okay, so you know what a membrane is made of. A key concept is fluidity. Membrane fluidity. Okay. We want our membrane to be able to, and things in the membrane, to be able to move around. Okay. Even though we draw our cells like this, and maybe we draw a protein over here, well, it might need to move over here. Or several of them might need to clump up together to respond to the environment over here. So your membrane has to be fluid enough that things can move around, but not so fluid that nothing moves. And I should say start over. It needs to be fluid enough so that things can move around, but not so fluid that it falls apart. Right? So it's this fine line of, again, think of making Jell-O. Jell-O starts out as this watery thing, and you can't put any fruits or vegetables in your Jell-O when it's all watery. They'll all sink to the bottom, right? And then as it cools down, it starts to become more and more semi-fluid, and then you can put marshmallows and fruit and stuff like that, and they stay suspended. The problem is, once Jell-O becomes that semi-solid that you're ready to eat, things can't move around. So for membranes, they want to find that sweet spot between liquid and Jell-O, or what it says over here is viscous, something so thick. So membranes can control fluidity a couple of ways. And the first way is by using saturated and unsaturated fatty acids. Right? So if you have a lot of fatty acid tails with kinks, they can't pile up really close and you can get very liquidy. And if all your fatty acids are saturated, they can pack really tight and you can become too viscous. You can become too solid. So a membrane has to have a mixture of unsaturated and saturated fatty acids to have that nice fluidity. So that's the saturation effect. Or you could call it the unsaturation effect. The length of the fatty acid tail or chain can also affect fluidity. So this means the number of carbons, right? So over here on this side of the graph, it shows you that, and instead of worried about transition temperature, this is from cell biology, more fluid to less fluid, okay? As you decrease the chain length, the number of carbons, it becomes more fluid, okay? That's because you have now more room for things to move around. Okay, again, it's all about, can you pack tight or not so tight? Okay, so if you decrease the chain length, the number of carbons on that fatty acid or on that phospholipid tail, you'll become more fluid. This side is showing you the number of double bonds. So this is saturation effect. And you can see as you increase the number of double bonds, you become more fluid really fast. So chain length has a small influence on membrane fluidity. Number of double bonds has a large influence. So you put 3 kinks in that chain and you become very fluid. Temperature has an effect, just like temperature does on everything. The higher the temperature, you increase the temperature, molecules have more energy and they're going to move around a lot more. So you're less tightly packed, you're more fluid. When you increase the temperature and you become less fluid at lower temperatures. Now, we maintain a specific body temperature where our membranes are, so temperature doesn't affect us that much. But there are some organisms that have what we call homeoviscous adaptation, and they can increase the number of double bonds if they need to make their membranes more fluid. And they can decrease the number of double bonds, or they can increase or decrease the number of the chain length. Or what I'll show you about next is the effect of cholesterol. So these organisms who are subject to temperature out in the environment and can't control their internal temperature have to actually adjust their membrane composition, the fatty acids in there, depending upon the outside environment. Pretty cool stuff. Finally, cholesterol. So remember that cholesterol is that lipid. It's shown in yellow here with the 4, and I'm not drawing a good structure, 4 ring structure. So it's not a big carbon, 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 carbon chain. And cholesterol does have an OH group, a hydroxyl group, which you know gives it a partial charge. That makes it a polar molecule. Everything else here is just carbons and hydrogens. So cholesterol will always orient itself with the little polar piece right there, and then the rest of the lipid in the membrane, right? Just like the phospholipids have their polar head and their lipid tails. So cholesterol is really interesting. So what you can see here is that when you shove cholesterol into a phospholipid bilayer, it takes up space. So cholesterol takes up space in a membrane. So what is its influence on fluidity? Well, it depends on the temperature. So, without cholesterol, okay, these are both membranes without cholesterol. So in the cold, it's rigid, it's not as fluid flexible, right? It's packed tightly because we said temperature decreases fluidity. So if you add cholesterol, then you actually start shoving these phospholipid molecules apart, and adding cholesterol in the cold makes the membrane more fluid, right? So you're taking something tightly packed and you're making it space out a little bit. So you'll make it more fluid. Quite the opposite in warmer temperatures. Without cholesterol, as it's drawn, your membrane is going to be too fluid. It's got all this energy. Things are moving around. So add cholesterol. And now you take up that space and it decreases fluidity. Both is because cholesterol takes up space. In something that's tightly packed, it takes up space and makes it more fluid. In something that's loosely packed, it takes up space and makes it less fluid. And the way researchers measure membrane fluidity is the TM, called the transition temperature. Again, this is an important concept in cell biology, but I just want to show you it here, that the transition temperature is this sweet spot where you're not too solid and you're not too fluid. And when you add things like more unsaturation, you become more fluid than something without a double bond. So that 18 stands for number of carbons in the chain. And the ... 1 or ... 0 is the number of double bonds. So if this is 18 and 0 with a TM of 70 degrees, and when you add one double bond, your transition temperature drops way down, which means now at 16 degrees is the sweet spot between gel and fluid. Since this membrane's transition temperature is 28, it most likely has shorter tails. Right? Oops. So it might be 16 and 0. Or it might be 20 and 1. We don't know where it is between these two lipids, but it tells you that it has a pretty low transition temperature. And remember that body temperature is 37 degrees Celsius. So you want your membrane fluidity, that sweet spot, to be around 37 degrees Celsius because that's your body temperature. And that brings us back to this concept of the fluid mosaic model, which just means that a membrane, so there's my cell and my red line's my membrane, and say these are different proteins in my, let's see if I can draw, I'm not going to be able to draw this, phospholipid bilayer. Okay, that's just getting too messy. And the fluid mosaic model means things can move around in a membrane. This is what I was talking about at the very beginning of this little video. The membrane is fluid enough that things can move around. And think of this as this big 3D sphere that proteins can move from any side of the cell to another side to interact with the environment because the membrane has fluidity. The mosaic means it's made up of a bunch of stuff, right? There's different stuff in the membrane. Some talk about mosaic being a pattern, but this pattern can always change. So we're usually talking about proteins here. Whoops. Sometimes we're talking about specific lipid types, but the fluid mosaic model, which I can't find a super great video, but all of these are really quick videos I suggest you watching, is this great concept that this membrane on the cell, things can move around from region to region, and that a membrane, cell membrane, is not just lipids, but a mosaic of other things. You need to understand how or what a membrane is made of in order to understand membrane transport and how and why things can or cannot cross a membrane. And membrane transport is what we will talk about in class.